Hello and welcome to this presentation on multimodality and how to use Hugging Face to achieve it. So multimodal models are essentially models that can input two or more modalities. In this context, we are talking about multimodal computer vision, and there are many types of multimodal computer vision models. The first one is the vision language model. Vision language models used to mean that a model can understand image and text at the same time, but not necessarily output anything. But currently, vision language models are models that can input image and text and output text. Biggest example to vision language models are GPT-4V or Lava. The second type of multimodal models is mask generation, but it doesn't necessarily input text. It rather means that you have an image, and in that image, for instance, you might have a dog or cat, and you might want to segment that dog. So you either draw a bounding box around that dog, so essentially you pass the model the bounding box coordinates of that box, or you leave a point prompt, which means the point coordinates inside that dog, and the model can segment the dog because it has learned about the real world. And the third one is the open vocabulary or zero-shot image classification, object detection, and image segmentation models, which can input text and image, and depending on the type of the model, it can either output the image class, detected objects, the bounding boxes, or the segments of the objects that you want to segment. So this is what I meant when I was mentioning about the old vision language models that can understand image and text. CLIP consists of an image and text encoder, and these encoders are trained jointly, as in the outputs backpropagate to both of the encoders. Essentially, it was trained to take both image and text input. The model assigns high score to the image and text pairs that are most similar to each other. So essentially, the text that describes the image the most are paired together, and they have the highest score. And this is the objective that CLIP was trained on. And the least similar ones are sort of pushed away by means of score as well, and this loss backpropagates to both of the encoders. So what can we do with CLIP-like models? With CLIP, you can do many things. The most outstanding use case of CLIP is to do zero-shot classification, where you can input an image and candidate labels for that image, and CLIP will assign a higher probability score to the most similar label for that image. And these labels are just open-ended, because CLIP is not restrained to any label that it was trained on. That's why it's called zero-shot image classification. But these models, like CLIP-like models, are used to train many other zero-shot models, and also models like Stable Diffusion. CClip is a model released by Google DeepMind, and it is still state-of-the-art, and it is essentially a CLIP model with sigmoid activation, and it was used to train many models that I will talk about today. You see here CClip in action for zero-shot image classification. OLD is a zero-shot object detection model that followed the similar approach to CLIP, and essentially you input an image and you input a candidate label, and the model just outputs bounding boxes to whatever you wanted to detect with the text prompt. In here you can see this model is also used for tracking if you wanted to use it for. And you can use it to fine-tune for your own object detection dataset, and it would likely perform better than any other backbone. Before moving on with open vocabulary segmentation, we have to talk about mask generation. So mask generation, as I have talked about it before, essentially is to input an image and the bounding box coordinates or a point comp coordinate of what you want to segment in the image, and to get the segmentation mask. And most powerful model for this is Segment Anything, that was released by Meta. And this model was trained on 1 billion masks, so it's pretty much a universal segmentation model. Open vocabulary or zero-shot image segmentation is to input a text and an image and get the objects that we are talking about in that text. And there are many ways to achieve this, but as of today, the most successful way to do so is to combine a zero-shot object detection model and a mask generation model. Because the mask generation models do not really accept any text inputs, we pass our image and our labels through the zero-shot object detection model and get the bounding boxes for those labels, and just pass the bounding boxes and the image to the Segment Anything model to get the segmentation masks for those objects. And lastly, most important type of multimodal models are vision language models. And these models essentially take any text input and an image, and can understand image and text and reply accordingly. These models can essentially do anything, but the most important use cases can be the visual question answering, image captioning, document understanding, and more. These models generalize very well to a point where you can train them on detecting objects inside an image, and they output bounding box coordinates in the output text. So one can create any vision language model by combining the large language model of their choice and the image encoder from, for instance, CLIP. The image encoder part of the CLIP is connected to a multimodal projector. So what happens is that you have this image encoder and you have the output embeddings. And this multimodal projector sort of projects those embeddings to the embedding space of the large language model. Projected embeddings are concatenated to the text embeddings, and then they are passed to the text decoder. So these models go through firstly pre-training and then fine-tuning. During the pre-training, you take a pre-trained image encoder. It can be, for instance, CLIP's encoder or CLIP's image encoder. And then you take a language model. It can be any language model of your choice. It can be Mistral, it can be Llama, it can be anything. And then you connect them with a multimodal projector. And you freeze the image encoder and text decoder and only train the multimodal projector so it can learn how to project those embeddings. And later when you do the fine-tuning, you can choose what you want to unfreeze. So most of the time what people do is that they freeze the image encoder and then they train the multimodal projector and they train the text decoder as well. They sometimes also do LoRa fine-tuning, parameter efficient fine-tuning on the text decoder parts. But if your images in the fine-tuning dataset are very far to the images that were used to train the image encoder, you might want to also unfreeze the image encoder and just do a whole fine-tuning. So there are three different types of vision language models. The first one is the base models that are only sort of pre-trained. And then you have the chat models that are base models fine-tuned on chat data, mainly the conversation turns. And third one is the instruction models that are base models that are fine-tuned to follow instruction. And now I will go through some of the most prominent vision language models of these days. First one is Polygemma that was released by Google. So the authors of Polygemma have released pre-trained models that can be used for fine-tuning. And this is the main use case of this model. Mixed models that are fine-tuned on a variety of tasks, and lastly, fine-tuned models that are fine-tuned on single task. And this model requires fine-tuning. So if you would like to use it on chat, for instance, you have to fine-tune it on chat. This is a very good model for fine-tuning because it converges very well if you would like to fine-tune it on your downstream dataset. And this is, to my knowledge, the first model that can do segmentation as well. This model was built using CLIP's image encoder and the Gemma model by Google. So you can see the mixed model in action here, segmenting different objects in the image. You can do essentially any task, but I wanted to show this because I think this is really cool. Another cool model is Cosmos 2 by Microsoft, and recently Microsoft has released Cosmos 2.5. It's a vision language model with grounded pre-training, which means that there are less hallucinations with this model, and it can also do object detection. And to my knowledge, this is the first model that could have done object detection as a vision language model. Another model is IDFX 2 by Hugging Face. It comes with chatty, instruct, and base versions. One thing that is very cool about this model is that you can insert image tokens to where you would like to mention about the image. So it's not like you have multiple images and you just feed them. This model also comes with superior document and mathematic capabilities. So DACOL is a document understanding model released by Alibaba. And document understanding, if you do not know, is very much beyond OCR because documents are more complicated than that. So documents have the layouts of components inside. They have the text, they have charts, they have images, tables inside. So it requires much more than OCR itself. And cool thing about this model is that the visual encoder consists of a bit-like model and then there is a convolutional model in parallel. So this is more attentive to low-level details and thus performs way better than many other document understanding models. And this is a trend we have seen with vision language models recently. Lastly, there is a new model in Transformers called Video Lava, which is like lava but can understand video. And all of the models that I have mentioned before this model are available on Transformers to use, except for DACOL, which will come to Transformers very soon. So you can use Transformers to fine-tune and do inference or optimized inference with these models. There are many vision language models on Hugging Face Hub, and you can filter them using image text-to-text filter that you can see on the left tab in the tasks. You can also find other tasks like zero-shot image classification or zero-shot object detection here as well. And you can also find models like Blip on image-to-text. For vision language models, it might be very overwhelming trying to find the right model for yourself. So there is OpenVLM Leaderboard, where you can see all the vision language models and how they perform on the benchmark of your choice. So for instance, you might select multiple metrics that you care about and even get the average score and rank the models that you would like to see. There is also closed source models behind APIs ranked, so you can compare them. You can also check which model is suitable for your hardware and just filter for those models according to your hardware. There is also Vision Arena by AI that was released where people are blindly choosing model outputs. So these models are ranked by preference. This is just like LMS's chatbot arena, but for vision language models. So once you find your model, how can you deploy this? You can use text generation inference toolbox. It is mainly used for large language models, but text generation inference can also be used for vision language models. It comes with many optimizations, it has quantization support, it has tensor parallel inference and more. And if you would like to customize your model, needless to say, you can use transformers to do so. I have previously mentioned, but many of the multimodal models are implemented within transformers, so you can fine-tune them on your own datasets. Another library is Transformer Reinforcement Learning, TRL. This is normally used for LLM alignment. However, for vision language models, it has a supervised fine-tuning support that you can use. Another library that is used a lot is parameter-efficient fine-tuning, that is used to do parameter-efficient fine-tuning. You can do LoRa and QLoRa and more to come for vision language models using PEFT. And lastly, you can use Quanto for 248-bit float 8 quantization on different hardware. And Optimum, it has static quantization, dynamic quantization, many graph optimizations for a big variety of hardware. You can shrink any model of your choice that exists within transformers. And lastly, this is my project called Small Vision. And Small Vision includes many example notebooks for quantization, fine-tuning, anything that you can think of for multimodal models and normal vision models, but mostly multimodal models these days. So please check it out in my GitHub. And if you have any questions, feel free to ask in comments and also join us at Hugging Face Discord, and I will see you again.